Hello, in this video we're going to talk about value at risk, what is value at risk, and how to measure value at risk. And this will be done for two concepts, one assets, or we can calculate the value at risk for our portfolio. Before, we need to remember some definition from statistics. Two main definitions is the mean and the standard deviation. The mean of the returns is the sum from 1 to t of all the returns divided by the number of observations, and the standard deviation, which is the formula associated with the returns in deviation from the mean in square root. So with the mean and the standard deviation, we are able to calculate the value of risk with different methodologies. So let's start with one asset. Let's suppose that we have one stock. And we have a sequence of prices, could be an index, a stock index. So to calculate the return and the standard deviation, we use the mean and the standard deviation from the data, as we have in the formulas above. So the sequence of prices that we have allow us to calculate the standard deviation of the mean returns. With this information, we can generate the value at risk. So first, let's begin answering the question, what is value at risk? Value at risk is a measure of potential losses in the value of an asset or a portfolio, given a certain period of time and a certain probability. And we need to emphasize that this value at risk is a expected concept, so it is associated with the potential loss, the value of an asset, and the probability associated with those events. For instance, let's draw the returns of an asset. We have time and returns, and the red line is the return of the asset. So the value at risk will be associated with the downside risk, the negative returns that we have here in the green. So how do we measure this value at risk? We have basically three methodologies. One is historical simulation. The second is associated with a normal distribution that is called the delta normal method. It's assumed normal distribution for the returns. And the third is the Monte Carlo simulation. We're going to review the first two in this video. So first, historical simulation. For the historical simulation, is based on actual historical data. So we have the returns of the data, and we need to estimate the VRR using a kind of sorting and ranking of the historical returns. Let's assume that we have the histogram of the return for one asset. Let's draw that. We know that the histogram is usually drawn with bars. I'm doing this in a continuum assumption, so this would be the red. So we have a non-normal distribution, but it's just an histogram, a continuous histogram. So the idea of the value at risk is to measure the probability of getting returns below some level. So for instance, in the historical simulation, we rank and sort the returns and measure the 5% of the probability density function from the left. So for instance, in this case, here we have the 1% of the data, but also we can have the 5%. That is usually the benchmark for the value at risk. So we have, let's suppose that this point is 2.8. So the value at risk in 5% is 2.8 negative. This means that with 95% of probability, the return of the asset will be higher than minus 2.8%. But alternatively, we can say that with 1%, with 5% of probability, the return of the asset will be minus 2.8% or lower. Let's see the second methodology, that is the delta normal VAR. Using the standard deviation calculated from the data we define above, uh, and assuming that is the base of this methodology, assuming returns normally distributed, we know from the normal PDF that if we multiply standard deviation by a sector factor, we can get different level of confidence intervals. For instance, for 5%, we need to multiply sigma by 1.65. So in our case, let's suppose that we have a standard deviation of 2%. Then the value at risk of 5% will be equals to phi times sigma times the square root of t. The square root of t is associated with the frequency of the data. For daily data, this would be 1 if you want to calculate the VAR for 1 day. Sigma is our standard deviation, and phi is the C coefficient for normal PDF. That we have phi is equal to 1.65 with 5% or 2.33 for 1%. So our VAR for 1 day with 5% will be equals to 1.65 times 2, that is associated with a 3.3%. The meaning of this is that 95% of the probability the return of the asset will be higher than minus 3.3%. But also we know that with 5% of probability the return of the asset will be minus 3.3% or lower.